of e to the power of t1 x1 plus e to the power of t2 x2. You remember in a joint distribution in 4600 also we said t prime x, where x contains two random variables, and which works out to be a things like that. So it's a known result. You have done it. You can complete your notes and move on. There is nothing new that I'm talking here for this particular case. So the moment generating function of x1 and x2 is the expected value of e to the power of t1 x1 plus e to the power of t2 x2. And by definition of the moment generating functions, it is this one, e of t1 x1, e of t2 x2, and this is the joint density what we wrote earlier. All right. So even if it is cut, doesn't matter, not very important. So it is the same guy what we wrote earlier. And then the x1 is from 0 to n and x2 is 0 to n minus x1. Now, when you simplify this stuff, this is all simplification exactly in the same manner as I did here, except that when you have e of t1 x1, I coupled this one with p1 to the power of x1. So basically this and that term together give you et1 times p1 to the power of x1. That is what you see here. Similarly, this is coupled with that and you get this term here. There is nothing, you write this as it is. And all these things are there, the summations are there. And we are manipulating this also exactly same as before, just that instead of just P1, you have here P1 ET1. And in this case, first is this. This is same as what you got earlier, P2 plus P3 to the power of, it is this one, where you had P2 plus P3 to the power of n minus x1. In this case, it will be P2 ET2 plus P3 to the power of n minus x1. So it is the same working, we are doing it, just that these terms are slightly different. So this is P2 E2 plus P3 to the power of, so it is the same step what we did earlier as well. So you need to revise the binomial as well. And then this also same as where I wrote P1 plus P2 plus P3. In this case, instead of P1, I have ET1 P1, and this is same as that. So the binomial A plus B to the power of n has been applied twice in this case. And that brings you the result to be the moment generating function of the joint distribution of x1 and x2 is e to the power of t1 p1 plus p2 e of t2 plus p3 to the power of n. It's a very nice mathematical stuff, and I would encourage that you expand yourself. It will give you better understanding of these distributions. If you are doing mathematical statistics, you can't get away from this kind of theoretical work. You have to have good skills to understand and recall and develop all these things. And it is expected from you. Take my word, it can be a part of your any test or quiz or exam, whatever it is, so that one is testing your skills through these theoretical results. So we have found the moment generating function of the joint distribution of x1 and x2, and now from there I put my t2 to be 0, and that gives the moment generating function of the first random variable x1. Okay, so we put t2 from a joint distribution. This is how you find the moment generating function of any marginal distribution. So first I put here t2 as 0, so it reduces to that, which is the MGF of a binomial random variable. Do you recognize it? You have done the MGF of a binomial random variable earlier in your third year course and match this one with what we have found here, and the conclusion is this. So the conclusion is the random variable x1 is binomial
The probability of success is P1 and the number of trials is N. So you see, we were looking at the joint distribution of x1, x2, where x1 stand the number of experiments which resulted in outcome 1 when the trial was performed n times. So we have found that the marginal distribution of x1 is binomial. This is what we have found, is binomial with the probability of success is p1 and n as usual. Similarly, and therefore we know that the mean of x1 is np1, a known result, and the variance is this one. All right. Similarly, I did not write it down. You can write down the marginal distribution of the random variable x2. That also, as you have seen from the joint moment generating function, it is also binomial. The parameters are p2 and n. All right. So the two marginal distributions of x1, x2 are found to be binomial, and therefore we can find out the mean here, the variance of each one of the two random variables. So this was an introduction of the sampling model trinomial, but binomial and trinomial, and here I will give you a general case, and that's my last result here. So we have talked of the sampling model binomial. We have talked of the sampling model trinomial. Okay. And now finally, you can have an experiment which results in, say, in general, K outcomes. Okay. So it can be, let me give a nice example to you. Suppose you have a data set of the, what should I say? What should I say? Okay, suppose if you look at grade 12, Ministry of Education, they have data from 2001 to 2025. And the data tells you, because in the list you will have a student, only one student who got the highest marks in grade 12 countrywide. Okay, so say first year of your study in your data 2001, and you say Mishek Banda, he got the highest marks in grade 12 countrywide. Okay, and he belongs to the northern province. Okay, you are working on some data. You can write down. So I have the data from 2001 to 2025. Is that okay? And 2001, you will say the top candidate came from the northern province. The first, the person who got the maximum marks in grade 12, he came from the northern province. 2002, the person again came from the northern province. 2003, it is the northwest, and things like that. You will have 25 such data points. Okay, so it means that the trial here is that in any year in grade 12, the top performer can be in one of the 10 districts. You see that can be from the southern province, the northern province, the Luapula, Lusaka, Copperbelt, and so on. So here I'm talking about a multinomial experiment, that is the a student or the student who got the highest marks in grade 12 countrywide, and you will attach with this student his or her province. Okay, so this is an example for a multinomial distribution, and you can look at the probabilities. Pn means the probability that the student came from the northern province, and then P of L means the student came from the Lusaka province, and things like that. So when you have data for a large number of years, say 50 years, because Zambia started their education, say, I do not know, but maybe from the year 1965. So we have 60 years of data. So the data is huge enough to estimate these probabilities. Probability that the top performer came from the Lusaka province or the top performer came from the copper belt and so on. So you will count the 60 years of data, how many years we had the best performer from Lusaka. Suppose it is 7. So the probability for Lusaka will be 7 over 60, an estimate of the probability will be 7 over 60. And say for the copper belt, 6 students were the top performer in the data. So probability of the a student coming from the top performer coming from copper belt, and an estimate of this probability will be 6 upon 60. So that is how you can do that. So this is just an example of a trinomial or a multinomial distribution where an experiment can result in more than 2 or 3 or maybe k categories. In this example, the categories are our districts. Any question before I move on and explain to you this slide? Anybody wants to ask any question from here?
No, no
Okay, so
question.
when I'm taking a general case, I'm saying here a trial is performed which results in one of the k possible outcomes. Okay, here I took the outcomes as the k districts. That is the top performer or the best performer belongs to which district, isn't it?
Mm-hmm.
And pi is the probability that outcome I is resulted in the ith, that the let pi be the probability that outcome I is resulted, that is in an experiment outcome I is resulted. Okay, suppose the trial is performed n times, xi is the number of trials resulted in the ith outcome. So there you write this probability. Do you see that? We are talking of k outcomes. So the first outcome resulted in little x1, the second outcome resulted in little x2, and so on. And this is the probability. You can think of these conditions as I did before, generalize yourself, because it will be p1 to the power of x1, p2 to the power of x2, p3 to the power of x3, and so on, pk to the power of xk. So you can write the generalization very easily. And from the trinomial distribution, finally, you have k random variables here, discrete random variables. And so the conclusion is that each one of them, the marginal distribution is binomial. Okay? And the expected value of xi is npi. It is like in the binomial distribution, the expected value is np. This was my first question in quiz 2. It is just to reinforce these ideas. I gave that question in quiz 2. So this is the mean, this is the variance, this is a bit long way to go. I'm not talking about that. So we have talked today about a trinomial distribution. We expanded it, doing all kinds of properties of that. And from there, we arrived the marginal distributions of x1 and x2. And finally, we generalized a trinomial distribution to a multinomial distribution where the categories are k. I think I am done with these sampling models for now. The Poisson, binomial, trinomial, and in general, a multinomial distribution. And that was what I wanted to talk today. And I will expect your answers for quiz 2 so that I can mark and assign you numbers. I'll sort out why I'm not able to share a Word document with you. I do not know. I'll explore. So, any questions, students?
No question, madam. When are we supposed to submit the answers for the quizzes?
Where you are supposed to?
Submit the answers for the quiz.
No, 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 as soon as possible so that I finish my marking by the weekend.
Okay.
All right, but make your notes also. The supplementary materials are there, and little bit what is missing on my right side or left, I think it is, you can write out yourself the way I've explained to you. But if you still want to confirm, then you have the supplementary materials and they will guide you. Am I done now? Anybody wants to say anything? Otherwise, I close the session. I think I've done for today. So, in my next lecture, I will start estimating the parameters in these sampling models. Because you have talked about the Poisson model, and the parameter there is mu, which is the average occurrence per unit of time. So we have to estimate it from the data. Similarly, in binomial, we have to estimate P, the probability of a success. And I've already given you an example of these 10 districts. And then to find the probability that the top performance comes from Lusaka province. So I've already spoken with that one, but that is what we are going to do. And so we will have the next topic will be, so I've finished the first topic, which is the categorical variables and their sampling models. So this topic is done. And from next week, I will start the estimation of the parameters in the sampling models. So I close the session unless somebody asks me anything. Okay, but last time you did help me so that today we were not disturbed by the students. They are joining freely, which is good. But somebody can explore that why I'm not able to share my Word document. I will also see, I'll ask my colleague why it's not happening because we might need it, but let's see what happens. So,
Okay.
thanks for coming. I close the session. Thank you.
Thank you. Thank you.